earlier sodium, right? We had to take a look at sodium. When we write the electron configuration for sodium, it's Na. And the short way would be use the noble gas that's right before it. So it would be neon. And then it would be, this here again represents the s orbital. This here is the p orbital. This here is the d orbital. And this down here would be the f orbital. Or sorry, subshells. This here actually is just a placeholder for that, where the F would fit into the D shell. Okay. So in this case, this guy would be 3s1, right? So when we talk about valence electrons are those electrons that we can use for bonding, right? Or that are freed up for bonding. And so we only have one electron available in the case of sodium. So we would draw the Lewis structure of sodium as Na with a single dot. Okay. Now, if we had looked at oxygen, if we do the electron configuration for oxygen, that guy is going to be O. And then we have, move this over a little bit. Then we'd have our core, which in this case would be helium. And that core, again, represents all electrons that would build up to helium. And those electrons we're not going to use, right? So really all you're using are the S and the P that gets us to oxygen. So in this case, it'll be 2s2. So there's 2 electrons. This superscript here represents the number of electrons. This here represents the period. And then 2p4. So oxygen has these 2 electrons and these 4 electrons that it could actually use for bonding. So in this case, oxygen would have 6 dots around it. Okay. So to be like a noble gas, oxygen, which is right here, it needs to get 2 more electrons. So it wants to try to have a total of 8 electrons around it. That means it reaches its octet. So oxygen is going to either share electrons with someone. And so usually you share electrons with atoms that are also, well, in this case, nonmetals. Nonmetals are going to share electrons, okay? Where if you get it from a metal, the metal usually wants to give it up, right? Because it doesn't want to share, it wants to get rid of electrons, okay? So if you have a nonmetal and a metal together, they form what we call an ionic bond, okay? And I'm going to show you that here in a second, okay? But first, we kind of got to understand that we need to understand how to figure out the number of valence electrons, okay? So if we look at carbon, the easiest way to determine the number of valence electrons is to look where carbon is at, right? And how far is it from being a noble gas? So if we count, that's 1, this is 2, this is 3, this is 4. So carbon needs 4 electrons, right? So that means that carbon has 1, 2, 3, 4 valence electrons. So carbon would only have 4 dots. Do you understand that, Maria?
Yeah, I get it now. So we just like, so what the dots means is like it just determines how far they are from being a noble gas.
Yeah, in a sense, it tells us how many electrons we have, and then how many, it gives us an idea how many more we need to get to. Like, so for instance, if we look at arsenic is down here, right? And we're not going to pay attention to the d orbital. We're only going to pay attention to what the s and the p, right? So we're going to only count the ones in the s and the p. So if we count for arsenic, As, it has, okay, it has 1, 2, 3, 4, 5 valence electrons. So it would have 5 dots around it. Okay, and then if we look at it, it's only 3 away from being a noble gas. So if it gets, I'm going to put this in a different color, if it gets these 3 electrons, it's going to be like a noble gas. Okay, so if it gets this guy, that's 1, 2, 3. So it needs 3 more to be like a noble gas. So arsenic is going to try to be like a noble gas because that's more stable. So when it comes in contact with the metal is going to want to give up the electron. And arsenic, in this case, arsenic is a metalloid. So it has characteristics of a metal and a non-metal. So sometimes it's going to act like a metal, and sometimes it's going to act like a non-metal. So in this case, it's going to act like a non-metal when it's kind of around a metal. So then it's going to want to get those electrons from the metal. So if we take a look at calcium, calcium has 1, 2 valence electrons. Do you see that? So you just look at the period that the element is currently at, and you just count the S and the P, and that tells us the number of valence electrons, and that's how many dots we're going to have. Okay?
Okay.
That's the easiest way.
Is there like a chart for this and like maybe in our book?
Yes, it's actually in your notes, chapter
Okay.
11. It's actually chapter 11 and chapter 12. So,
Okay.
and it's also in your book. Okay, so we're talking about, as I said, chemical bonding. And the more you're exposed to it, the better off you're going to be. So when you start doing the homework, it'll start making sense. And you need to look over the notes that we take, right? As well. So I talked to you guys about that give and take, right? So that means if we pay attention to what I said, we're exchanging electrons, right? And do you guys remember the charge on electrons?
Isn't it negative?
That's right. Electrons are negatively charged. Okay, so if we have sodium, and I like using sodium because it's really easy, it has that 1 electron, right? And if sodium gets rid of that 1 electron, then it doesn't have any electrons around it, or it has what we call 8. It reaches its octet. It's happy. It's stable. Okay, so the idea is that sodium wants to be like neon. Let's see. So sodium wants to be like neon. Right? So sodium wants to get rid of that 1 electron, so it'll be just like neon. Okay. Now, the way that it gets rid of the electron is by giving it away to like a non-metal, right? So there's an exchange going on. Now, if it gives it away, right, then sodium is going to have a plus charge. So sodium is going to have a plus charge associated with it. Now, this plus charge makes it what we call an ion. Okay, an ion is just basically a charged element. Okay, so, and this is a particular type of ion. We would call this guy a cation ion. People look at it and they'll say cation, right? We call it a cation because it's, quote, positive, right? Pa, meow, pow. You get it? I guess not. It's a bad joke, okay? I know. Okay, so cations are always going to be positive ions. So it's going to be positively charged ions. And then we have what we call an anion. Can you guys see the green type?
Yeah, I can see it.
Okay, so if we take a look at fluorine, fluorine is here. Okay, fluorine needs to needs to gain one electron to be like neon. So fluorine needs to gain one more electron to be like neon. And if it gains that electron, fluorine is going to have a negative charge. Okay. And so this guy would be called an anion because it has a negative charge associated with it. Okay. Be clear. Okay, so cations are going to be positively charged ions, and they're going to be formed by when the element or the atom loses one or more electrons. And anions are negatively charged ions, and they're going to be formed by gaining electrons. Okay, so remember, I said the way that you get stable or the way that you become like the noble gases is to either gain electrons, lose electrons, or to share electrons. Okay, so if we take a look here, this here basically shows us the, in the case of nitrogen. So nitrogen has 7 protons and 7 electrons. So if we look at nitrogen, it has 5 valence electrons around it. And these are the valence electrons. It's in the 1s, I'm sorry, it's these last two represent the valence electrons. So that 1s2, which is in that first orbital, is the same thing as neon. So that's like that neon core. Okay. So it has 5 valence electrons. So that means it needs 3 more electrons, and then it'll be just like neon, right? And we would say that this guy is called isoelectronic to neon because it has the same number of electrons as neon. Okay. So if we look at the periodic table again, let's see, why won't you work? 1 second. So we look on the periodic table again. Here's nitrogen. So 1, 2, 3, 4, 5. So nitrogen has 5 valence electrons. Now, for it to be like neon, it needs to gain 3 more because we want to get to what we call our octet. We want to have 8 around us to make us stable. Okay, 8 or none. Okay. Does that make sense? Or do we need to give another example? Yes. Okay. So if we take a look at oxygen, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. So oxygen has, as I said earlier, 6 dots around it. 1, 2, 3, 4, 5, 6. Okay. So it needs 2 more to be like neon. And so then it would be isoelectronic to neon. And so again, we know that the noble gases are noble because they're stable, right? They basically have what we call their octet filled, or their outer shell is completely full. And so that's the way that all of the elements that are in the main group want to do. They want to try to get it so that their octet is full, either by losing electrons or gaining electrons. Okay. Okay, so again, so that means that oxygen would need 2 more. And then if oxygen has those 2 more, then we have O2 minus. Okay, for fluorine, fluorine needs 1 more. So fluorine has 7 valence electrons around it. It needs to gain that 1 electron. And when it gains that 1 electron, that means that it's like a noble gas. It's like neon, and it's happy and it's stable. And in that case, it's going to have a minus charge because we added one additional electron, one more electron compared to the number of protons. Okay, and if we look at neon, neon is totally happy. It has 8 valence electrons in that outer shell. So it has 8 around it. So it's like, it's cool. It's like, I'm good, you know? So it doesn't want to add anything else. Okay. Are you guys good so far?
Is it possible for it to have more than 8 valence electrons?
Yes, it is possible for it to have more than 8 around it, but those are exceptions. And we'll talk about those a little bit later, I promise. Then you're going to want to throw darts at me because you're like, man, it was just so much easier when we were just talking about those 8 around it. Okay. Let's see. Okay, so this here is basically showing you which monoatomic ions are isoelectronic to what. They're based upon colors. So if you take a look at hydrogen, hydrogen becomes isoelectronic to helium if it gains 1 electron, where lithium becomes isoelectronic to helium if it loses 1 electron. All the ones here in blue, these guys are all going to be isoelectronic to neon. Nitrogen, as it gains 3 electrons, it's going to be isoelectronic to neon. Oxygen, as it gains 2 electrons, it's going to be isoelectronic to neon. Fluorine, as it gains 1 electron, it's going to be isoelectronic to neon. Sodium, if it loses 1 electron, it's going to become isoelectronic to neon. Magnesium, as it loses 2 electrons, it becomes isoelectronic to neon. And then aluminum, as it loses 3 electrons, it becomes isoelectronic to neon. Okay, so this is kind of like showing you how things are going to become similar to the noble gases. Okay, and that's by either gaining electrons or losing electrons. Again, if you're that metal, you're going to be losing the electrons. And if you're that non-metal, you're going to be gaining electrons. Okay. Okay, so we'll see how much you guys remember. It says, write the electron configuration for calcium ion. Okay, so first off, let's take a look where calcium is at on the periodic table. So calcium is located here. So if we write the electron configuration for calcium, and we're going to use the core concept. So what is going to be my core? What is going to be the nearest noble gas before calcium? Okay, so calcium is located here. So we want to go to the nearest noble gas that's before calcium, which is, what noble gas is this guy? Argon, that's right, argon. So we have calcium, and we'd write in brackets, argon. And then we come down to the 4, and it's 4s2. Okay, so calcium has 2 valence electrons. So for it to be like argon, it has to lose those 2 electrons, right? So if we're writing the electron configuration for calcium 2 plus, we can just write it as argon. Or we could actually write out the whole thing for calcium 2 plus. So in that case, if we write it out the full way, we start up here, where we start off with the first, that first period. So it'll be 1s, and s can only hold 2 electrons. If you guys recall, I know we've been out for a while, so that takes care of that. And then we have 2s, 2. Then we have 2p6. Then we have 3s2. And then 3p6. So that would give us the exact same electron configuration as argon. And that's exactly what happens when we lose those 2 electrons, we become isoelectronic to argon. Okay, questions? Okay, so let's go back to the slide. Okay. So this is it written the long way, like I said. And then, and this would be isoelectronic to argon. Okay, so then that brings us to the next thing, right? So I told you that the way that the metals lose their electrons is by giving them up, okay? So if we have calcium, which is 2+ when it forms an ion, and we have oxygen, which is 2- when it forms an ion. So what happens when you have a positive charge and a negative charge? Bring it close together. Have you guys ever played with magnets that are polar, meaning that they have a positive end and a negative end?
Yeah.
Okay. So if we put 2 positive ends together, what happens?
Isn't that when they like don't like connect, right?
That's right. They repel each other, right? Because then you try to push them together and they keep trying to push away from it, right? So they repel each other if it's 2 positive ends. If I have a positive and a negative, what happens?
Then they connect to each other.
Then they connect each other. And so the way I like to think about this is because, you know, and I think I've said this to you guys, I'm not 100% sure because, you know, it's all a big haze, but I like to think of it as relationships, right? So we think about our very early relationships, like we're in high school, and let's say you're that good girl, right? So you're real positive, right? And then the bad boy asks you out, right? And you're like, oh my God, Johnny asked me out, right? And you're like, you go home and you're like, Mom, guess what? Johnny asked me out. And you're just so excited and everything like that. And your mom looks at you and she's like, Johnny? You mean Johnny Jones? Johnny Jones from the Jones family? Those criminals, those thugs, right? And you're like, yeah, Mom, but Johnny's not like that. Oh, Johnny's just like that. The apple don't fall too far from the tree, right? You're that good girl. He's that bad boy, right? So let me ask you something. And I don't know, I could be wrong about this, but in general, what happened in that situation? Did this happen to any of you guys? Ever in high school or as an adult? Did you guys find that bad boy and you're that good girl, or you're that bad girl and they're that? Did that ever happen to any of you? Brittany?
No, I don't
Ever?
think so. I just think they were just dumb and like annoying.
So you never went after the bad boy, you're saying?
Yeah.
Okay. Okay, so you're an anomaly, right? So I think everybody's done it, right? Even when I was in high school, I don't know if I was a bad boy or if I was a good boy, but I always went after the bad girls, right? And so and it's just it's nature, right? Because opposites attract, right? So there's a tendency of opposites attracting. And so the way I think of it is, I think of it as kind of like relationship. These opposites are going to attract. So they're going to come together and they try to balance each other out, right? You're always trying to make Johnny that good boy that he's never going to be. And then Johnny keeps trying to make you that bad girl that you're never going to be, right? So it's always that balancing out. So am I the only person that experienced that? It's interesting.
I mean, maybe I experienced it to like some extent, but not like super crazy because I'm like, I don't know. It was weird.
Ah, so you're admitting a little bit now, huh?
Yeah.
Okay. I see. I see. Yeah. Okay. So that's kind of like what ionic compounds are. They're going to be the opposite charges that are going to be attracted to each other. So this case where we have our calcium who's plus and our oxygen who's minus, they're going to be able to come together and balance each other out completely. So in other words, they no longer, when they come together, they no longer have their independent charges. They work as a unit, right? They come together and their charges are canceled out perfectly, okay? So we end up with calcium oxide, okay? So the same thing happens in the case, let's say we had calcium, which is 2 plus, and we have fluorine, which is a single minus. So that means that to balance calcium out, we are going to need 2 fluorines, right? So she needs twins to handle her, right? So it's going to be CaF2. Does that make sense? So ionic compounds, they come together and they're attracted by the charges. And they come together and they have to balance each other out completely so that you have a total net charge of 0. So that +2 and that -2 is going to end up being 0 when it comes together. This +2 has to be balanced out with 2 single minuses so that it could balance it out. So we end up with calcium fluoride. Do you guys see that?
Is there ever like an occurrence where they don't balance each other out?
Yes, and that's when they form what we call a ionic compound, right? Or not an ionic compound. It still has an ionic charge associated with it. It does happen, but usually the only way that it happens is if you have a shortage of things, right? If you have enough of everything, it shouldn't happen. It should balance each other out. Does that make sense?
Yeah.
Okay. Okay, so okay, so a couple things that we want to know about ionic bonds. So this charge, right, the fact that we have this together, it brings these guys together. And in most cases, when they come together, they're going to form what we call they're going to form a solid ionic compound. Now, it's considered non-ionic compounds because they're made up of 2 ions coming together to balance each other out. Okay, and in most cases, almost all of the ionic compounds are going to be solid at room temperature. So at normal temperatures and pressures, they're going to be solid. And these solids are going to form what we call crystal lattice. So in other words, they're going to be organized so that, excuse me, sorry, trying to drink coffee and talk at the same time is not the best thing. So they're going to be organized so that you're going to have your plus charge surrounded by your minus charges, and then your minus charges surrounded by your plus charges. And I'm going to show you an example of that here in a second. Okay. So these guys, when they come together, they're going to have to be electronically neutral. Basically, they have to balance each other out completely, right? So in this case, these guys balance each other out completely. In this case, these guys balance each other out completely. Okay, so we had to have two of these guys, two fluorines, to balance out that +2 charge on the calcium. Okay, so this attraction, this ionic attraction is very strong. So that means that it takes a lot of energy to sit there and get these guys to separate, as long as it's not in water, right? So as soon as we put these guys in water, in some cases, not in all cases, in some cases, these guys will dissociate. They will break apart because water has what we call, and we will talk about this a little bit later in chapter 13 and 12, but water is polar, basically meaning that it has partial positive and partial negative characteristics. And so it'll be like a home wrecker. It'll come between the two ions and separate them from each other. Okay, and I'll show you an example of that later on too. So ionic compounds, when they're in their liquid form, so if we put a lot of heat, a lot of energy in there, we can make it into a liquid. When it's in its liquid form, then it's able to conduct electricity. It's really good at conducting electricity. And it's also really good also when it's in water because of the ionic character, those plus and minus charges. It helps conduct electricity that way. So they're really good conductors. Okay, so here's an example. So if we have sodium metal, and so sodium metal, when it's with chlorine gas, so we have chlorine gas, Cl2, plus that sodium metal, is going to make sodium chloride, NaCl. And you guys remember we have to get this balanced. Okay. So this guy's a solid. This guy's a gas. And this guy's a solid. So what happens is, is that sodium gets rid of its valence electron, right? So it takes its valence electron and it kicks it out basically, and then chlorine picks it up. So this electron gets kicked out and given to chlorine. So then chlorine becomes Cl minus, and sodium becomes Na plus. So then these guys they come together by charge, they're attracted to each other, and then they become sodium chloride. Okay. Are you there, Vernice? Are you guys seeing that? Okay, good. Okay, so this is just basically showing you that in a much beautiful way, right? So here, it has that one valence electron. That electron is then given to form the chlorine ion. So here's chlorine, then it gains that one electron. So it has 17 electrons total. It gains that one extra electron. So now it has a negative charge associated with it. Where sodium had 11 electrons, it loses one electron. And so now it has 10 electrons. So it gave up that one electron to make chlorine happy and then to make itself happy. Okay. And so these guys form a lattice by altering between This guy here represents the sodium. This represents the chlorine. So the gray represents the sodium, the green represents the chlorine. So they're alternating between positive and negative charges because this guy is positive, this guy's negative, this guy's positive, this is negative. So they alternate between them. Okay, and they form a nice crystal lattice. Okay, so this is basically a salt crystal. This is just basically showing you a different perspective of that lattice and more organized fashion. So this is that ball and stick modeling, and this is the space filling model. Okay. So, and you'll notice that here, this chlorine is surrounded by those plus charges, and then the sodium is surrounded by the chlorine ions. Okay, so this is just showing you that when we melt salt, so we put enough heat into it, we can actually melt salt. Takes a lot of heat, and then that's able to conduct electricity. So these guys are good conductors when they're in their liquid states or when we put them in water. Okay. So that's ionic bonds. So let's talk about covalent bonds. So covalent bonds are when we share electrons. So if we take a look at the periodic table, only our non-metals are going to share electrons. Okay. Okay. So the way I like thinking about this, it's kind of a weird way because the non-metals are all on the same side, essentially, except for hydrogen, which is a kind of a little bit of an eyeball. But I like to think of it as, you know, with metals, right? Metals are like on the other side of town, right? And non-metals on a different side of town. Okay, so if you had a neighbor who had this really cool bike, right? And not to say that anybody's thieves or anything like that, but let's just say I was a thief. Would it make sense for me to steal from my neighbor who lives next door to me his really cool bike? Or would it make sense for me to take away from somebody across town?
Somebody across town,
Why?
because if it's next door, it's going to be really obvious.
That's right. And he's going to call the police on me immediately. He's going to like, dude, you stole my bike, right? So, and I can sit there try to say, no, that's my bike, right? But he would know his bike is missing. And all of a sudden I get this brand new bike that looks just like his, right? So in that case, it would make more sense for me to sit there and say, hey, can I borrow your bike, right? Rather than me take his bike, right? So the way I look at it is that non-metals will take away from metals, where if you have two non-metals together, you're going to share, right? And that sharing has two possibilities. We could have even sharing or uneven sharing. How many of you guys have siblings?
I do. I just have one.
You have one? Okay.
Yeah.
I have two sisters, okay? And when I was growing up, my family, we basically lived from paycheck to paycheck. My family was pretty poor. My dad was in the military and everything, but he went to the military because his family was really, really poor. And my family was really, really poor overall. And so what we would get for Christmas, we would get one gift that we would share, like a really good gift that we would share. And then we would get socks and underwears that we would basically have to use for school and stuff, right? And so that's just kind of the way it was and the way I kind of grew up. So one year, my parents went all out and they bought us, and this is going to date myself, they bought us an Atari. Do you guys know what an Atari is?
I've heard of it, but is it a gaming system?
It is a gaming system. Okay, yes, it's like the PlayStation or the Nintendo Switch, right? But back in the day. So my parents bought us an Atari, and the rule was that we had to share, right? And so I told you that my parents were poor. My dad would go out on the boat because again, he was in the Navy. And so it was like he had just went out. He came home for Christmas. He went out back on a boat. So my mom basically was working, again, trying to make ends meet and everything like that. And she kind of worked two jobs. And so what she would do is she would work. And so I'd be responsible for watching my sister. So during Christmas break, she'd be working, all the time and everything like that. She'd come home, and my job was to cook and make sure that the house was cleaned up. And so I would cook so that she'd have something to eat when she got home, and then I would make sure that me and my sisters had the house clean for the most part. And so she was like, "Well, you guys have to stay in the house and everything like that because we were young and everything, but we couldn't afford a babysitter and stuff. So I was responsible. So they bought us this Atari, and the rule was we had to share the Atari. Okay, so now I'm a smart guy for the most part. I do some dumb things every once in a while. So I thought about this. My mom said we had to share, right? So the way it worked was that when my mom was at work, I would play the Atari up until about, let's say, about an hour before she got off of work, because then I'd go in the kitchen and clean and cook and clean up, and then and then as she's coming in, she'll see my sisters playing the Atari, right? So I played the Atari all morning and all afternoon, and then as soon as my mom comes in from work, she sees my sisters playing the Atari, so we're sharing, right? And then so soon as she comes in and everything like that, I'll say, oh, after she saw my sisters playing, I said, okay, it's my turn. And then my sisters, that's not fair. That's not fair. I said, Mom, look, they're playing the Atari. I should get to play it now, right? Because I let them play it. And then I said, we're sharing, right? And so for the longest time, we're sharing, right? In my mind, I was obeying my mom's rule. So were we sharing or were we not sharing?
I don't know. Maybe I guess, kind of, not really. It's such an older sibling thing to do because I'm the
It is.
youngest.
Yes. I'm obviously the oldest, if you can't tell. So, yes. So it is sharing, right? But it's uneven sharing, right? Because I got it 90% of the time and they got it 10% of the time, right? And so that is called, now let me type this down, polar covalent. Polar covalent bonding. Okay, so polar basically means that you're sharing, but you're sharing unevenly. Okay, so it's uneven sharing. Sharing of electrons. Okay, so if we were sharing evenly, where they would get it part of the time and I would get it the other part of the time, so it was 50-50, then that would be called nonpolar covalent bonding. Okay, and so that would be even sharing of electrons. Okay. Okay, so let me give you an example of both. So we have oxygen in water sharing an electron. So the way that we would draw sharing is a line between the two elements. So oxygen sharing electrons with hydrogen, right? So there's one electron or two pairs of electrons being shared between oxygen and hydrogen, two pairs being shared between this oxygen and hydrogen. And so this sharing is uneven. So that basically means that the electron is going to spend more time around the oxygen than the hydrogen. So this guy, this is delta. This represents delta. So this means that oxygen is going to have what we call a partially negative charge because you have the electron spending more time around the oxygen than it is spending around the hydrogen. And this guy is going to be partially positive. Okay, so when we're talking about ionic bonds, those were when we gave up electrons or we either gave up or we take electrons. We're either giving or taking in that case, right? Here, you're sharing. And so you could have that uneven sharing where it's not shared between them evenly. And so that means that the electron is spending more time around one than the other, kind of like me with the Atari, right? I got the Atari 90% of the time. My sister's got it 10% of the time. So we're sharing it, but it's uneven sharing. Do you guys get that? Okay. Brittany, are you with me? Okay. Okay, so we have those partial positive and partial negative that are going on there. Okay, so that's an example of polar covalent bonding. So water is considered to be polar, right? So it has those partial negative and partial positives. Now, those partial negatives and partial positives could sit there and interact with things that are negative and positive. So that's what happens in the case of when you guys put salt in water. So what happens when you guys put salt in water? Anyone? You guys have never put salt in water?
I have.
What happens when you put salt in warm water?
Isn't it like dissolving?
It dissolves, right? So it dissolves because you're going to have your sodium, which is positively charged, interacting with your partial negative charge of oxygen. And then your chlorine ion is going to be interacting with your hydrogen, which is partially positive. And so it separates it. So kind of like thinking of water like a home wrecker, right? It goes up to sodium and says, you know, sodium, hey, baby, you don't need chlorine. You got me. I'm good, right? And then at the same time, it goes over to chlorine and says, hey, baby, you don't need sodium. You got me. So it splits them up, right? The home wrecker. Okay. Do you guys see the analogy?
Yeah.
Okay. So that's the reason why we're able to dissolve salt in water, right? So as long as we have enough water, right, to dissolve all the salt particles, then we're good, or the salt molecules. Okay. Let's see. Let me erase. Okay. So again, this is an example of polar. So water is an example of polar covalent. Okay. So an example of non-polar covalent bonding is, you guys heard of methane? Cow's fart? Yes, no, maybe? Yes, no? Okay. Methane, the chemical structure for methane is CH4. So you'll notice carbon normally has 4 valence electrons. I should probably show you guys this at some point. And hydrogen has 1 valence electron. Hydrogen wants to be like helium, so it wants to have a total of 2 electrons around it. So it's going to be sharing its 1 electron with one of carbon's electrons. And so each of these hydrogens are going to share one electron with carbon. So it'll be 2 around the hydrogen, right? So it's sharing it so that it can reach its octet. So it acts as if it's like helium because that electrons it's sharing with carbon. So then it has 2 around it, just like helium. So it's kind of like a noble gas in that case. This one has 2 electrons, just like helium. So it's kind of like a noble gas. And that's the same thing. Now, hydrogen will only want to have 2 electrons around it, right? So you're only going to get 1 bond from hydrogen, okay? So hydrogen can only form 1 bond with something. So hydrogen will never, ever be a center atom. Now, carbon, and I'm going to say this, and you guys are probably going to yell, carbon is friendly. Carbon's a little bit of a whore. So carbon likes to have 4 things around it if it can, right? So it could have 4 bonds around it. So again, it has a total of 8 electrons surrounding it. So it's sharing that 1 with each of the hydrogens, and it had the 4 that it's also sharing as well too. So that's 2, 4, 6, 8. So these lines represent 2 electrons that are being shared, or bonding electrons. So that's 2, 4, 6, 8. So it's like a noble gas because it's like neon now because it has 8 around it. Okay, do you guys get that? Yeah, no, maybe? Okay. Okay, now these guys, since you have all of these hydrogens around them, so they're all pulling evenly. So this guy is actually being evenly shared, okay? So, you know, carbon is like, okay, so you get it part of the time and I get it part of the time. You get it part of the time, I get it part of the time. So you have even sharing between hydrogen and carbon of the electrons. And so this guy is called non-polar covalent bonding. Where this guy, oxygen is kind of like the big brother and says, okay, I get it the majority of the time and you only get it a little bit of the time, okay? And so if we take a look at the structure here, oxygen has 8 electrons around it. So that's 2, 4, 6, 8. So it's happy. So it reaches its octet. And then the hydrogen has the 2 around it, like it likes to be like helium. So they're both happy. Okay. Are you guys with me so far?
Kind of.
Kind of. If there's a question, this is a great time to ask a question. No, then we can keep going with the lecture.
Can we like have like, oh, I don't know if everyone agrees with me, but can we have like another like example of like the 2?
Sure. Let me erase this. So we have this. Okay, so we have hydrogen and fluorine. So these guys, fluorine has 7 valence electrons. So it wants to reach its octet. So it's going to share 1 electron with hydrogen. So then that gives us 2, 4, 6, 8 around it. This guy has 2 around it. So they're both happy. Now, fluorine is a bully, right? Fluorine is very, very strong. So, you know, like we were talking about how oxygen is kind of like the bigger brother. Fluorine is like the big brother that is just a bully all the time. So he wants to try to take it or get the electrons towards it the majority of the time. So it has the electrons surrounding it a lot of the time and only a little bit of time with the hydrogen. So in this case, if we went showing the polarity, this guy would be partially negative. This guy would be partially positive. Now, the negativity electronegativity of this guy, it's going to be really great because the electron is going to spend a whole lot of time around the fluorine and only a little bit of time around the hydrogen. Okay, so again, this guy is going to be a polar covalent compound. And then let me give you an example of a nonpolar. Easiest one ever. So when we have two atoms that are exactly the same, so diatomic elements like iodine, these guys are non-polar because they have even pull, so they're as evenly strong. Have you guys ever played tug of war? No? You know what it is? Where you have one group has a rope on one side, the other group have a rope on the other side. And in the middle of the rope, there's like usually a flag or something like that. So it looks like this. I'll show you my art skills here. See, these are things that I can do in class that I can't do online. It's really hard. Okay, so this is the rope. Okay, and there'll be a flag in the middle, like right here. So that represents my flag. Okay, so the goal is try to get the flag on one side or the other, right? So if these guys are even, right, they're as strong as each other on both sides, then the flag is going to stay in the middle, right? So that's what we're seeing in the case of nonpolar covalent bonding. So nobody is stronger than the other, okay? Now, if I'm going to draw my, if let's say the red team is stronger than the purple team, then what's going to happen is that the flag is going to be moved towards the red team, right? So that means that these guys were stronger than the purple team, so the flag moved towards them. So that meant the electron, if we think about the electron is being pulled towards the guy who has the strongest. And what we're talking about the strongest, we're talking about the electronegativity. The one that has the strongest electronegativity is going to be pulling the electron towards it. If the electronegativities are close to each other, right? So then the flag is going to stay in the middle, so they're going to share evenly. If one is strong, if one atom is stronger than the other atom in terms of electronegativity, then it gets pulled towards it. So in this case, fluorine is strongest. So it's going to be pulling the electron itself. So the electron is going to spend more time around fluorine than it's going to be spinning around the hydrogen. Okay, does that make sense? Okay, good. Okay. Here. Okay, so molecular compounds are basically compounds where we have covalently bonding. Okay, so they're molecules rather than ions. So in other words, one is not giving up the electron; they're actually sharing the electrons. Okay. So here's just basically showing you the Lewis dot structure of how we would draw the bond between hydrogen, since we know that hydrogen is diatomic. So hydrogen only wants to have 2 electrons around it. So they're going to be sharing those 2 electrons between the 2 hydrogens. Each one is providing one to share. So it forms a single bond. Okay. So when we talk about conductivity, the ability to conduct electricity, so solutions that are covalent don't conduct electricity, right? So water doesn't conduct electricity. So I should say water that doesn't have any ions in it doesn't conduct electricity. Sucrose or sugar, table sugar, doesn't conduct electricity because it's covalently bonded. But table salt, when it's put in water, will form ions, and so it's able to conduct electricity. So in actuality, when we talk about that sharing of electrons, what's happening is that you have these electron clouds or these densities of electrons that are orbiting the nucleus of the atoms. And so what happens is that your orbitals are going to actually overlap, okay? And so then that allows you to sit there and share. And so if you have half full orbitals with just a single electron in it, because each orbital can hold 2 electrons, what's going to happen is that you can actually share electrons, and you could end up having electrons from, let's say, another atom that will actually form that bond. And so you're actually sharing the electrons by orbiting both of the atoms. Okay, so here's an example of that. So here's that cloud density for hydrogen. You can see the electron here, and this represents the electron cloud. This is the electron cloud for the other hydrogen. And so this is the electrons orbiting both nuclei. Okay. So this is the Lewis structure. So in the case of fluorine, fluorine is also diatomic. So it takes 2 fluorine to make our diatomic element for fluorine. And so both of these guys want to have 8 around it. So they're going to share 2 electrons. So we have a bond forming between those 2 fluorines. And so that's 2, 4, 6, 8 surrounding this fluorine, 2, 4, 6, 8 surrounding this fluorine. Okay. How are you guys doing?
So like the line in between like the fluorine just represents the bond, like they're sharing a bond, like that's what it symbolizes.
That's right. And it represents 2 electrons. Okay. Now, let's take a look at oxygen. So if we take a look at oxygen, oxygen is also diatomic. It has 6 valence electrons. So if we have another oxygen, which also has 6 valence electrons, and remember, the goal is to try to get it so that you have 8 electrons surrounding you. So you're going to share electrons, so you end up with 8 around both of the oxygens. So if I did that, right, let's say I'm going to take these 2 electrons here, actually. So then that would give me, move those towards the center for sharing, right? So then that would give me, it's not the right color. Okay, so then that would give me 6 around this one if we were sharing those 2 electrons. So that's 2, 4, 6, 8 around this one, but this guy would only have 6. Now we want to try to get it so that it has 8 around both. So that means that we're going to have to actually take 2 from this guy as well too, and share. Okay, so that'll be a total of 4 electrons that are going to be shared. Okay, so in that case, let me draw what that's going to look like. And since only two electrons considered an orbital, so in this case, we have what we call a double bond. Okay, so then that's, again, the line represents two electrons being shared. So that's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 8 around this oxygen. So in this case, we'd have to form what we call a double bond so that everybody reaches this octet. Okay, where with the fluorine, we only have to form a single bond. Do you guys see that? Maria?
Yeah, I see it. It also reminds me of like the simulation, like where the like triple bond, I guess, there's like 4 lines and like stuff like that.
Triple bond would be 3 lines, right? So if we take a look at nitrogen, nitrogen is also diatomic. Nitrogen has 5 valence electrons. Okay, so what I'd like you guys to do is, let's connect this nitrogen so that both of them have 8 electrons around it. Kind of like what I did with the oxygen. So Bernice, can you write on my board? Or do you have a Chromebook? Oh, you have a Chromebook. Okay. So how many electrons are going to be shared between the nitrogens? That's right, 6. So it's going to form a triple bond. Okay. Do you guys see that? Hey. How are you? Good. I'm in the middle of a lecture right now. So, I'll come and see you. Okay. Okay, so do you guys see that? Yeah. Okay, good. Okay. So things that we want to keep in mind, okay, and terminology. So when we talked about that triple bond that's formed, we have these 2 electrons. So these electrons are called lone pairs. So these are electrons that are not going to be used for bonding. So these are pairs of valence electrons not used for bonding. So these are considered lone pairs. Okay. And again, we want to obey the octet rule, meaning that we want to have 8 electrons surrounding each of the atoms. So that's 2, 4, 6, 8 surrounding this guy. 2, 4, 6, 8 surrounding that guy. Okay. So we're going to make it a little bit harder now. So you guys are getting an idea of how to use Lewis dot structure. So what happens when we have something like, we'll start off with carbon monoxide. Okay. Carbon monoxide. How many valence electrons does carbon have? How many dots would it have? Did I lose everyone? Is it just you and me and Maria?
I think because like people are typing in the chat.
Okay.
Um, Isn't carbon just, I think it's one, right?
No.
Oh,
Okay, so let's take a look at the periodic table. Let's see. So carbon is right here. So we count till we get to carbon. So that's 1, 2, 3, 4. So it has 4 valence electrons.
okay, I got it.
Okay. Okay, so carbon has 4 valence electrons. So we're going to put 4 here. And oxygen has how many? Yeah, I think it's just me and you. I think we lost everyone. Oxygen has how many?
Is it 6?
That's right. It has 6. Okay. So altogether, we have 4 plus 6, so we have a total of 10 electrons to work with. So the goal is to try to get it so that each of the atoms have 8 electrons surrounding it. So let's say we pull these together, do this. So then that gives me my 4. So that would be, we'll take 2 from here. Okay, so right now, this guy has, that's 2, 4, 6, 8, 10. So that's a total of 10 electrons. So, but that's only 2, 4, 6 around carbon. So we're gonna have to make another adjustment. So we're gonna borrow 2 more from the oxygen. So we get C triple bond to the oxygen. That's 2, 4, 6, 8 around this carbon. 2, 4, 6, 8 around this oxygen. You see that?
Yeah.
Okay. So if we have something like carbon dioxide, now we have to decide which element is going to go in the center. So the way it works typically is the one who has the weakest electronegativity. Now, a quick way of determining electronegativity is we have a table that we actually use, but we'll get to that here in a second. Another quick way of determining electronegativity is, excuse me, when they're on the same period. So we have like carbon and oxygen, right? So if we have carbon and oxygen is what we're looking at in terms of CO2, the one that is furthest away from the noble gas is going to have the weaker electronegativity. So oxygen is going to be stronger in electronegativity than carbon. And you said you had siblings, right? You had a older sibling?
Yeah.
Okay. So I have 2 sisters, right? So I'm the oldest of 3 kids. And when we went on road trips, somebody always had to sit in the middle, right? So how do you think we chose who got to sit in the middle or who had to sit in the middle? Because it's not an honor.
Was it by age?
It was by age, but it was also by who was strongest, right? I was the strongest. So my little sister would always try to sit in the seat, and then I just push her over. I'm like, nope, you're going in the middle, right? And so my little sister would always get pushed in the middle, okay? So the guy who's the weakest in terms of electronegativity will always be the center, okay? Except hydrogen, because hydrogen can never, ever be the center atom. Okay, so if we take a look here, we have carbon, one carbon, two oxygens. So we're going to put carbon in the center. So carbon goes in the center. Carbon has 1, 2, 3, 4 valence electrons. Oxygen has how many?
6.
2, 3, 4, 5, 6. And the other oxygen has the same. 1, 2, 3, 4, 5, 6. Okay, so we have 6 times 2, which is 12, plus 4. So we have a total of 16 electrons to work with. Okay, so we want to make sure that we have a total of 16 electrons surrounding all of the atoms together, but we want to try to fix it so that we have 8 around each. So what should I do in this case? Everywhere here.
Is this when like get to start like making bonds and stuff like that?
Yep. So how are we going to make bonds so that everybody has 8 around them? How many are around carbon right now?
Is it just 4?
It's just 4. So what can we do so that we have 8 around carbon?
Add 4 more?
So we can't just add them. So we have to take them from somewhere because this is the total number. We have 2, 4, 6, 8, 10, 12, 14, 16. We only have 16 to work with. So we can't add more than what we don't have.
Oh, so can we like take 2 from each oxygen?
Okay, so we'll take 2 from each oxygen. So I'm just going to circle these in orange. That's not a good color. It's funny how great it looks on my screen, and then when I try to put it on the big screen, it doesn't look the same. So you're saying take 2 here and take 2 from here. Okay, so now we have one, 2, 3, 4. Okay, so then that gives me 8 around that carbon. Do we have 8 around each oxygen? Let me draw it like this. So like that.
Yeah.
Okay, so that's 2, 4, 6, 8, 10, 12, 14, 16. So that checks out. So we're good there. Okay, so that's 2, 4, 6, 8 around this oxygen. That's 2, 4, 6, 8 around carbon. That's 2, 4, 6, 8 around this oxygen. Everybody's happy. Piece of cake?
Yeah.
Okay, good.
Because the end result is just what you want to get from what you started out with, right?
That's right.
Okay.
Yeah. And making sure that everybody has 8 around them except for hydrogen, which only wants to have 2 around it. Okay, so let's do another one. Let's do NH3. Okay, because hydrogen can never, ever be in the center. Who's going to be in the center?
Nitrogen?
Nitrogen. Okay, how many valence electrons does nitrogen have?
Is it 5?
That's right. Okay, so that's 1, 2, 3, 4, 5. I'm actually going to be a little cheat here. Okay, how many valence electrons does hydrogen have?
Is it 1?
Okay, so it's 3 times 1. So we have a total of 8 electrons to work with. So we have hydrogen. Oops, hydrogen. Hydrogen. Okay, so what am I going to do now?
Is it to make sure like each one of them have 8, right?
Yep, except for hydrogen, which only has 2 around it.
Okay.
Okay, so let's go ahead and draw these lines because that's going to be sharing. That's going to be sharing. And that's going to be sharing. So do we have 2 around this hydrogen?
Yeah, because of like the line represents that.
That's right. And then this hydrogen
Yeah, we have 2.
and this hydrogen.
Yeah.
Okay, and how many do we have around the nitrogen?
Is it 2?
It's also 2? Count, because this line represents 2, right? So that's 2, that's 4, that's 6, 8. That's right. That's it.
Okay.
So this is what this would look like. So it has 1 lone pair, and then it has 3 bonds, 1 to each hydrogen. Okay. Okay. So we talked about polar covalent bonds, right? So polar meaning uneven sharing. And then we talked about nonpolar, which means even sharing. Okay, this is just another example of showing you that, right? So nonpolar is when things are being shared evenly, right? Polar is when this guy gets the electron more than the X. And then ionic is when you're giving a complete transfer of electrons. Okay, so this guy becomes a negative charge and this guy becomes a positive charge. Okay. Okay, so electronegativity. So let me show you the table. This is the table for electronegativity. So as we go from left to right, we increase in terms of electronegativity for the most part. There are a couple of exceptions. And as we go from top to bottom, we decrease in electronegativity. Okay. Now, fluorine is the most electronegative element, right? Oxygen is the second most electronegative. Francium is the weakest electronegative. Okay, so they're like total opposites. Fluorine very strong, francium very weak. Okay, so the rule is, if we're looking at bonding, polar bonding, so the bond between, let's say, hydrogen and oxygen in the case of water, right? So one of those bonds, so if we look at the electronegativity between each of those and we take the difference between them. So the hydrogen, you see hydrogen here? Okay, it has electronegativity of 2.2. 2.2. Oxygen has a stronger electronegativity, so we're going to put that first. So we're going to be 3.4. So the difference between the two is 1.2. 1.2. So that means that the bond between hydrogen and oxygen is going to be a polar bond. So let me give you the parameters. if the difference between the electronegativity is less than 0.5, oops, that's the wrong way, less than 0.5, so we'll say difference. Okay, so if the difference between the electronegativity is less than 0.5, then it's going to be nonpolar. If it's 0.5, if it's greater than, oops, sorry, that is totally wrong. Okay, Pac-Man eats the bigger one, my bad. It feels like a Monday morning to me. Okay, so if the difference is less than 0.5, it's going to be nonpolar. If the difference is greater than or equal to 0.5, but less than or equal to 1.8, it's considered polar. And then if it's greater than 1.8, it's going to have ionic character, meaning it's going to act as if it's an ion or it's going to be an ion. Okay, so let's say we take a look at nitrogen and oxygen. Okay, so a bond between nitrogen and oxygen. So nitrogen is 3.0, oxygen is 3.4. So 3.4 minus 3.0 equals 0.4. So is that going to be polar or nonpolar or ionic character?
Is it nonpolar?
That's right, nonpolar. Okay, you see how to use that?
Yeah.
Okay, good. Okay, clear. Okay, and this basically just shows you that what we just talked about. Okay, we've talked about single bonds, double bonds, and triple bonds already. So the sharing of 3 pairs of electrons, sharing of 2 pairs of electrons, and sharing of 1 pair of electrons. We've already shown when we have more than 1 atom, we actually use the ammonia as an example earlier. Okay, so let's talk about the exceptions. So if you have an odd number of electrons in the molecule, so for instance, nitrogen has 5 valence electrons and oxygen has 6 valence electrons. So 5 plus 6, that equals 11. Oops. So there's no way that we can surround it so that everybody reaches its octet. So what we do in this case is that we make sure that the one that has the strongest electronegativity reaches its octet. The other one is going to be deficient by 1 electron. So for instance, here we have oxygen, it has 2, 4, 6, 8 around it, where nitrogen has 2, 4, 6, 7 around it. So nitrogen will always going to be 1 short, where the oxygen is definitely going to reach its octet because oxygen is stronger in electronegativity than nitrogen. Okay, does that make sense?
Yes.
Okay. So and this is another example of showing you exactly the same things. This guy has 2, 4, 6, 8 around it. This oxygen has 2, 4, 6, 8 around it, and it has a total of 2, 4, 6, 7 around them. So this again is an exception to the octet rule. Okay. So we have what we call hypervalence. Hypervalence basically means that you don't obey the octet rule. You're able to have more around you. So if we take a look at the phosphorus here, it has 2, 4, 6, 8, 10 around, where the fluorine has 8 around it. Okay, so there's the reason why that you're able to do this with phosphorus is because phosphorus is in the 3rd period. So anything in the 3rd period or higher, any period higher than 3, has the ability of having more than 8 around it because it can use those d orbitals. Okay, so those d orbitals allow us to sit there and put electrons there so that we would satisfy the compound that we want. Okay, and then in this case, fluorine is actually kind of pushing it because fluorine wants to make sure that it has 7, and this guy had 5 fluorines around it. They want to make sure that they get their octet fill, and so they're going to push phosphorus to do that rather than them having to share more than that 1 electron, right? So remember, fluorine's kind of a bully. It's going to be pushing things to that. Okay, so this is an example of hypervalence. So if you see something that has more than 8 electrons around it, it's called hypervalent. Okay, and this only happens in the 3rd period or greater. So things that are in the 2nd period won't do it. Okay, so you'll never see this with nitrogen or oxygen. Okay. Okay, so the other exceptions are this guy is called hypovalence. Or deficient, octet deficient. Okay, so beryllium is a metal, but it actually behaves sometimes like a non-metal. So it's kind of confused. And so beryllium will form a covalent bond with fluorine, with 2 fluorines. And it likes to have 4 electrons around it, and just 4, and that's it. So it's cool with just having 4 around it, and it's happy about it. So, but this is deficient because it's octet deficient because it only has 4 electrons around it rather than having 8 around it. And boron's the same way. Boron only likes to have 6 around it. So that's 2, 4, 6 around it. And so it's also going to be octet deficient or hypovalence. Okay. And the other exceptions, sometimes molecular oxygen has some weird properties. And so it becomes difficult to explain that. And so that can also be an exception to the octet rule. Okay. How you doing so far?
Pretty good.
Okay, so we're on that home stretch. We have 2 more slides. So the last type of bond that we're going to be talking about today is called a metallic bond. So a metallic bond is when we basically allow metals to come together, right? Or which we call alloys. Or it's just that one pure metal that comes together. And the way it works is that because you remember sodium isn't, it has one valence electron, right? Since it has that one valence electron, what it's going to do is it's going to delocalize that electron. So it's going to act like it's the sodium ion, so sodium plus, and it's going to put its electron, like drop it next to it, right? Like, so just drop it right next to it. And so then it acts like it's positive, and then the electron acts like it's negative, kind of like what you had with sodium chloride. But now you're just looking at a single electron. So this is called delocalization of electrons, or delocalizing electrons. Okay, now alloys do this. So alloys are just basically a mixture of two or more metallic elements. Okay, and we'll talk about that here in a second. Let me show you what that looks like. So this is my example. So this is my sodium. This is the electron that dropped next to it. That's the sodium ion. That's the electron that dropped next to it. And so it's kind of like just dropping that electron, pretending like that electron is an atom itself. And then it just makes what we call a sea of electrons, or electron sea, so that the electrons are just kind of positioned so that they act like a negative charge to attract that positive charge. And so that's how metals stay together. So that's a metallic bond. And so it happens the same thing like in the case of magnesium. Only thing in the case of magnesium, it's going to be 2 plus, and then it's going to have 2 electrons that it's going to be dropping. Okay, so here's the magnesium ion, and that's the 2 plus. Magnesium ion, that's the 2 plus. Magnesium ion, that's the 2 plus. So do you see that?
Yeah.
Okay. So a lot of the alloys that we use, like in real life, so like 18-karat gold, is just a mixture of metals. And they use this process of electron delocalization. So here, 18-karat gold is 75% gold, it's 12.5% silver, and it's 12.5% copper. Brass is also an alloy, which is just 60 to 95% copper and 5 to 40% zinc. Steel, stainless steel is an alloy. It's about 75% 70% iron, 18 to 20% chromium, and 8 to 12% nickel. Okay, and sterling silver is 92.5% silver and 7.5 copper. And so, like, stainless steel doesn't rust. The reason why stainless steel doesn't rust is because we have that chromium and that nickel there. If we just had that iron there, it would actually rust. Okay, and sometimes we would actually put in a non-metal in there, and so that's what carbon steel is, and that just makes basically steel a little bit stronger. So we can use alloys to kind of change that property of that metal to make it either stronger or a little bit weaker, depending on which metal that we're seeding with, or we can make it kind of resistant to rust in the case of steel, things like that. Okay, do you have any questions?
I probably have like one random question.
Okay.
Random question is like about like hypovalence and like how it could mean like deficient. So like
Yes.
say like I guess I don't know, but say like if someone's like has like is anemic, so like they're iron deficient, is that like a chemical like thing like that happens in your body then? Or is that not the same?
It's not quite the same.
Oh,
So in the case of them being deficient or anemic, the fact that they don't have the iron bonding, so typically that's a result of a mutation in a protein, so it doesn't allow the bonding effectively, or it just means that they're not taking enough iron in their body, so they're not taking enough of that iron ion to sit there and allow that's needed for the blood cells. So that's a little bit deficient, though. I mean, it's a little bit different than the hypodeficiency. So
okay. I was just
yeah,
curious because like that just reminded me of it, and I was just like, I just
yeah,
want to know.
yeah. But no, it's a good thought. It has the concept of it. The fact that you're lacking, right, is the same concept. In that case, you're just lacking the whole ion. So you're lacking that iron ion. So, but that's a little different.
Okay.
Yeah.
Just curious then.
Yeah.
And then
But it's a good thought.
for for this week's lab, will we just need what we needed last week then?
Yes. Yeah. We're gonna
Okay.
just do last week's lab. Yeah. And I'm sorry about last week. I was just, you know,
You don't have to apologize. It's okay.
yeah, it's always hard to lose a family member, and me and my cousin were pretty close too. And even though she's my grandma's first cousin,
Uh-huh.
she kind of took me in when I came out back to California, and she fed me and really kind of took care of me, kind of guided me in some things. So, you know,
Yeah.
yeah. So
Yeah. You don't have to apologize. Like, I completely understand. Like,
yeah,
I know what that can be like. It's really tough. But I hope you're
yeah,
doing better.
yeah. I'm doing better. It's always death is always a you never know how it's going to affect you until you have to deal with it, right? And
Right.
then even when you think you're dealing with it, you're really not dealing with it. And that's the way I've been. I've been trying to like be strong and kind of strong for the family. And then, but my mind has been everywhere, and I
Hmm.
see that a lot now. But I need to buckle back down because I have to get things, we have to make sure we finish a lot of things before the semester's over. So
Yeah. But take it easy on yourself still. You're doing good.
thank you. I appreciate that.
Okay. Well, that's all my questions then.
Okay. Well,
Okay.
on that, I'm going to let you guys go early today. So